Okay, so today is day 2 in the functions chapter, which is chapter 1. And today the thing that we'll be taking a look at is something called a piecewise function. So whenever you hear the term piecewise function, what that means is we're going to have a function that is defined by multiple formulas depending on the x value. So what you'll typically see is it'll start with an f of x. Now remember, f of x is function notation. That means you only get to use this if what's inside of here actually passes the vertical line test. So right off the bat, I already know what I have as a function and will pass the vertical line test, even though what's behind that looks rather weird. On the other side of the equal sign, you're usually going to see a big curly braces, and then behind the curly braces, you're going to see multiple formulas. Now, these things at the beginning, those are your formulas. And then you're going to see a comma, and what comes behind the formulas are the intervals over which you're supposed to use each formula. So remember, for these things to pass the vertical line test, we can't be putting two different y values with any of the x's. So we're going to be using one of the formulas or the other formula, but never both of the formulas. So for example, the way I would read this is I would use the formula x squared plus 1 anytime the x values are strictly less than -1. And I would be using the formula x minus 1 whenever the x values that I'm being given to plug in there are greater than or equal to -1. So there are two different things that somebody might ask you to do with piecewise functions. You could either evaluate your piecewise function at different x values, which is of course going to be easier, or a more difficult thing that you could be asked to do with piecewise functions is to actually graph them. So let's tackle the easy one first, evaluating a piecewise function. So what we're going to do here, whenever somebody gives us these function notations, like f of 3, f of -5, f of -1, remember the way that you're going to read that is we're going to evaluate our function when given an x value of 3. So one of the first things that has to happen when you have a piecewise function is you have to go and look at your interval and figure out which interval you're in so that you'll know which formula to use. An x value of 3 is most certainly greater than or equal to -1. So for this particular evaluation, I will be using the bottom formula. And again, remember, we've talked about anytime you're going to make a replacement in a formula, you should always use parentheses around it. So I'll be putting the 3 into the bottom formula where there used to be an x and then subtracting 1. So 3 minus 1 is 2. The second evaluation I'm doing is for f of -5. And remember, that means that -5 is going to be your x value. When I go to my piecewise function and look at the intervals, I realize that -5 is definitely less than -1. So that means this one should be using the top formula. -5, I'm putting parentheses around it, is going to get squared, and then we're going to add 1. So -5 squared is positive 25, plus 1 makes 26. Now the last one is one of the most tricky ones. -1, if you go back and look at your intervals, is actually the number at which we switch formulas. But when you look at the intervals more carefully, you realize one of them actually includes -1 and the other one does not. So we have to pick the formula where -1 is actually included, which is the bottom formula. Again, we're going to be putting parentheses around our substitution. So we have -1 and then -1 more, which makes -2. So this is how you would evaluate piecewise functions. Take the x value that they give you, look and see which interval you fall into, and then use the formula and plug that x value into it for only that formula. Never put your x value into multiple formulas at the same time when evaluating. Okay, that's the easy thing that we can do with piecewise functions. Now let's talk about the more difficult thing that you might be asked to do with piecewise functions. The more difficult thing is if somebody gave you a piecewise function and asked you to make a graph of it. So there are 5 steps to this process. The very first thing that you would do is start off by making an XY chart. So X is on the left, Y is on the right. I'm sure you've used this kind of thing before when doing graphing. The second thing that you're going to do is put the transition value into your chart twice as an X value, and then pick other X values on both sides of it. Now, the transition value is the number at which you're switching formulas. So in that last example, you remember the transition value would have been -1 because that's the number at which we're switching formulas. So you'd be putting your transition value into your chart twice, and then you'd want to pick some numbers that are smaller than -1 and pick some numbers that are bigger than -1 to put in your chart around that. The third step would be to find all the y values that go with all the different x values that you picked. Now remember, as you're doing this, as you're trying to find the y values, you're doing evaluation. So you first have to think about which formula it belongs in, and then do the substitution and work out the math properly. Step 4, you want to determine which value of which one of the points at the transition value is open and which one is closed from the inequalities and the intervals that you're using. And then fifth and final step, you're going to plot all the points and complete the graph. Don't forget to label your axes and the equation itself. So let's actually give this a try to see what this looks like. So in this example, we have a piecewise function, f of x equals, and you see two different formulas on the right-hand side. We see 2x minus 3, and we see -x plus 4. Both of those happen to be linear equations, so we know that they're going to produce straight lines. And then behind that, we see the intervals over which each formula is good for. The top formula is good for x values that are less than 3, and the bottom formula is good for x values that are greater than or equal to 3. So if we were asked to make the graph of this function, we would want to start by making an xy chart. That is step 1. Then what I'm going to do is I'm going to notice that the transition value in this problem, in other words, the place where I'm switching formulas, is an x value of 3. I'm going to put that in the middle of my chart twice. You may even want to, up to you, but you may even want to put a horizontal dividing line in your chart that's going to separate when you use the top formula as opposed to when you use the bottom formula. I want to pick some x values on both sides of 3. So I'm going to want to pick some numbers in my chart that are less than 3, maybe like 2, 1, and 0. And I'd want to pick some numbers in my chart that are going to be bigger than 3, maybe like 4, 5, and 6. This is going to force your piecewise function to have to use both formulas. You want numbers on both sides of 3. Okay, so now comes the evaluation part. For every x value that we've chosen, we got to figure out the y value that goes with it. And that involves also plugging into the correct formula. So for all of these numbers above my dividing line, I'm going to be using the top formula, 2x minus 3. We'll be plugging the x values in. So 2 times 0 minus 3 is -3. 2 times 1 minus 3 is -1. 2 times 2 minus 3 is going to be +1. 2 times 3 minus 3 is going to be 3. Then for the numbers that are below the dividing line, I'm going to be using the bottom formula. These are numbers that are greater than or equal to 3. So negating 3 plus 4 makes 1. Negating 4 plus 4 makes 0. Negating 5 plus 4 makes -1. Negating 6 plus 4 makes -2. Now at this point, if I were going to plot all the points that I have, you see that I have the same x value, 3, getting used twice. We know that that cannot be a function. You would not pass the vertical line test if we kept both of these points. One of these points is actually part of the graph, and one of these points is not. And the way you're going to figure out which one is included with the graph and which one is not included with the graph is you're going to go back and look at your intervals. The top formula actually did not include 3 with it. So that means this point of 3, 3 needs to be an open circle on your graph. We're going to go right up as close as we can possibly get to 3, but we can't actually be 3. So that means 3, 3 is going to be an open circle on your graph. And the bottom formula actually does include 3 with that little equal sign underneath the greater than symbol. So that means this point is actually part of your graph and should be drawn as a closed dot. Now, when you're drawing these points on your graph, I would make those two extra big so that you can definitely tell the difference as to whether they're included or not, open or closed. Okay, so now it's time to plot all the points and draw the graph. So I've got the point 0, -3, which is right here. I've got 1, -1, which is right here. I've got 2, 1, which is here. And then 3, 3, I'm going to draw a nice big open circle. And then I also have a point at 3, 1, which needs to be a closed circle. Make it extra big so you can tell. 4, 0, 5, -1, 6, -2. Now at first, these dots are going to look a little bit scattered. They're going to look like they're all over the place. But then remember, what you're actually doing is you're splicing together two different pictures. part of your graph is a line with a slope of 2 and a y-intercept of -3. That's this line. And the other part of your graph is a line that has a slope of -1 with a y-intercept of 4, but doesn't make it all the way to the x-axis. That's this one. Now, the one other thing that I want to tell you is about arrowheads. The top formula is good for all values of x less than 3. That means you could keep going to the left forever and ever and ever. So we're definitely going to want an arrowhead on the left of that, but you must stop when you get to 3, so no arrow on the right end of that line. And the second equation is good for x values that are greater than or equal to 3. So we don't want to put an arrowhead on 3 because that's where it's supposed to stop, but you're allowed to go as big as you want, bigger than 3. So we are going to put an arrowhead on the right of that. So this is our picture. Don't forget to label your x-axis, your y-axis, and somewhere on the graph, wherever it can fit, we're going to label the formula that created this, which was a big piecewise function. You've got to write. I know it's kind of annoying, but you're going to have to write all of this. Do not bother trying to put in each individual formula on its own part. That's not necessary. Just make sure that the entire equation gets somewhere on the graph, and then you're all good. Now we are going to practice tomorrow some more with making graphs of piecewise functions. This example only had 2 parts. We may see piecewise functions that have more than 2 parts, maybe 3 or 4. And so we'll do a little bit more practice with that tomorrow. But for today, that's all we're going to do with graphing piecewise functions. The next thing that I want to take a look at when working with functions is finding the x-intercepts of functions. And x-intercepts, another word for that is zeros. So you might also call these zeros or solutions or roots. So x-intercepts happen when your y value is 0. That's why they're called zeros. So basically what you want to do, if you're going to try to solve for the x-intercepts of a function, you basically want to set your function equal to 0. So if you're given these two functions, f of x and g of x being x squared plus 5x and g of x being 4x plus 6, if somebody were to ask you to find their x-intercepts and you were doing this manually by hand, you would want to take the formula for the function and set it equal to 0. Now this falls back on the tactics that we learned in the prerequisite chapter about how to solve different types of equations. This one happens to be a quadratic equation, so I'm going to try to factor it and then set each factor equal to 0 to get my answers. So x equals 0, x equals -5 would be the two answers for this problem. G of x being only a linear function means we're going to take that 4x plus 6 and set it equal to 0 and move the 6 over to the other side. So 4x equals -6, and then we'll divide through by 4. You're probably going to want to reduce this, so that's -3/2. Notice how linear equations only have one answer, while quadratics always have 2. Okay. So the last thing that we're going to do is talk about how to find points of intersection between two functions. So when asked to find the point of intersection between two functions, what you're going to do is set the formulas for the two functions equal to each other. So you take f of x, whatever its formula is, g of x, whatever its formula is, and then actually set the two formulas equal to each other. So again, using those same two formulas, f of x equals x squared plus 5x, and g of x equals 4x plus 6, if somebody asked you to find out when are the two functions equal to each other, you would literally take the formulas for each function, so x squared plus 5x, and you would set that equal to the formula for g of x, which is 4x plus 6. And again, we have to rely on the tactics that we learned in our prerequisite chapter. This happens to be a quadratic equation, and the first thing you're going to have to do is get it set equal to 0. So we're going to want to bring the 4x's over to the same side and the 6 so that you've got everybody on one side. So that would be x squared plus x minus 6. Now again, to solve a quadratic, we're always going to rely on factoring first. When we look at this equation, I'm trying to think of two numbers that multiply together to make -6 and add together to make 1. So those two numbers would be x plus 3 and x minus 2. And if those are your factors, that means your answer is going to be x equals -3 and x equals +2. So these are the x values that make our functions equal to each other. Sometimes they'll ask just what are the x values that make the two functions equal to each other. But sometimes one of the things that we might realize is that these are actually going to be points on a graph. This is the first formula is a parabola and the second formula is a line. So somebody might ask you where these points, where are the points of intersection for the system of equations? So if they ask that, you may want to plug the x's back into the formulas to find the y's that go with them. But if they just say to determine what x values make the functions equal, this would be all you would need. Okay, you are now ready to try the homework for tonight.